Thursday, August 27th, 2026. Welcome back. And today we're looking at something that on the surface might sound like routine California seismology, but when you actually line up the timeline, it stops looking routine at all. In the span of roughly 2 months, Southern California has experienced 3 separate distinct earthquake swarms, clustered around the same general stretch of desert, the same fault network, and the same underlying geological system that produced one of the most significant earthquake sequences the state has seen in decades. Individually, each of these swarms has been described by seismologists as not unusual. Collectively, 3 of them landing in the same region within 8 weeks of each other is exactly the kind of pattern that makes even calm, measured scientists start paying closer attention. This video is about what an earthquake swarm actually is, why it behaves so differently from the earthquakes most people are familiar with, what specifically happened in each of these 3 recent swarms, why they all trace back to the same seismic aftermath from 2019, what history elsewhere in the world has taught scientists about how swarm sequences can behave, and what this pattern of clustering swarms actually tells scientists about the state of stress sitting beneath this stretch of the Mojave Desert right now. Let's start with the most recent event, because it's what's actually prompting this conversation today. On Friday, August 21st, a series of earthquakes rattled the Coso volcanic field in Eastern California, prompting scientists to closely monitor the area for any signs of volcanic activity. According to the United States Geological Survey, 7 tremors were detected near Coso Junction by Friday afternoon, with the strongest registering a magnitude of 3, 4 at 10:26 in the morning Pacific time. The Coso volcanic field itself is a genuinely unique geological feature. Located roughly 100 miles northeast of Bakersfield, it isn't a single mountain or a single volcanic peak the way most people picture when they hear the word volcanic. It's a 150 square mile cluster of volcanic features, powered by a large zone of underground magma, containing dozens of vents and domes, along with active geothermal fields, fumaroles, and hot springs scattered across the landscape. This is a genuinely active geothermal system, one that has been harnessed for decades as a source of geothermal power generation precisely because of how much heat and geological activity sits beneath the surface in this specific stretch of desert. Now, on its own, this kind of activity at Coso is not new, and USGS and other monitoring agencies have been quick to point that out. The region has experienced swarms before, often as distant aftershocks triggered by larger earthquakes in the surrounding area. In fact, this connects directly to one of the most significant earthquake sequences in recent California history. Back in July of 2019, a massive magnitude 7. One earthquake struck near Ridgecrest, California, in that earthquake, along with its immediate predecessor, a magnitude 6. 4 foreshock triggered widespread aftershock activity across the surrounding region, including at Coso, which sits just to the north of the main Ridgecrest rupture zone. On the evening of July 5th, 2019, just about an hour after that magnitude 7, one main shock struck, a swarm began at the southern margin of the Coso volcanic field in Inyo County, triggered by a magnitude 5. 4 earthquake located roughly 20 kilometers east-southeast of Little Lake, itself very likely an aftershock of the larger Ridgecrest rupture. In the aftermath of that 2019 sequence, USGS scientists recorded an average of about 30 earthquakes per hour at Coso for an extended period, the overwhelming majority in the magnitude 1 to 3 range. Crucially, California Volcano Observatory scientists at the time specifically confirmed that no ground deformation indicative of volcanic activity had been detected, and that there was no imminent threat of an eruption, concluding that the swarm activity was tectonic in nature rather than volcanic, meaning it was being driven by fault movement and stress redistribution, rather than by moving magma beneath the surface. That 2019 sequence is genuinely the key to understanding everything that's happened since, because the Coso volcanic field sits directly adjacent to a broader network of faults that includes the Garlock Fault, one of the longest and most significant strike-slip faults in Southern California, running for roughly 160 miles across the Mojave Desert. This entire region, encompassing Ridgecrest, Coso, and the Garlock Fault, forms part of what geologists call the Eastern California Shear Zone, a broad, diffuse zone of faulting that accommodates a meaningful share of the overall relative motion between the Pacific and North American tectonic plates, working alongside the more famous San Andreas Fault system further to the west. Since the 2019 Ridgecrest sequence, this entire shear zone has continued producing periodic swarms. And according to detailed tracking of the region's seismic history, the frequency of these swarms has notably increased following the 2019 events. Historical data shows that only 2 distinct swarms were identified in this specific area between the years 2000 and 2018, one in 2009 and one in 2016. Since 2019, that number has jumped to 6 separate swarms, including 2 in 2019 itself, 2 more in 2025, and now further activity continuing into 2026. This trend strongly supports the working hypothesis among seismologists that the regional crust in this part of the Eastern California Shear Zone is still actively responding to the major stress changes triggered by the 2019 Ridgecrest earthquakes, more than 6 years after that sequence originally occurred. Now let's talk about exactly what an earthquake swarm actually is, because understanding this mechanism is essential to understanding why 3 of them landing in the same general region within 2 months is genuinely worth paying attention to, even when each individual swarm looks unremarkable on its own. As the United States Geological Survey describes it, a swarm is a sequence with relatively many earthquakes within a relatively small area that simply refuses to fit the more familiar mainshock-aftershock pattern most people associate with earthquakes. In a standard earthquake sequence, one large mainshock ruptures a fault, and then a series of progressively smaller aftershocks follow in a predictable, well-documented pattern of decay, gradually tapering off over the following days, weeks, months, or even years as the surrounding crust readjusts to the new stress state created by that initial large rupture. A swarm breaks that entire pattern. Instead of one dominant event followed by a clean decline in activity, a swarm produces a cluster of earthquakes that can hold steady or even increase in rate for days or weeks, sometimes with the largest earthquake of the entire sequence landing in the middle rather than at the very start. One useful way to think about the difference, as some seismologists describe it, is that a standard earthquake is like the snap of a dry twig, one sudden, sharp break. A swarm is more like a bag of popcorn in the microwave, many small pops occurring rapidly and somewhat unpredictably as energy is released in increments scattered across a wider area, rather than in one single concentrated snap. The scientific explanation for why swarms behave so differently from ordinary earthquake sequences points to what researchers describe as an extra ingredient that plain tectonic stress alone doesn't require: fluid. Water migrating through cracks and fractures in the crust raises what's called pore pressure, essentially the pressure of fluid trapped within the tiny spaces inside rock, and that increased pressure reduces the friction holding a fault in place, making it easier for the fault to slip. Critically, this process can feed itself in a self-reinforcing loop. A small earthquake makes the surrounding rock more permeable, opening up additional pathways. That increased permeability lets more fluid migrate through the rock. That additional fluid then trips more small earthquakes, and that loop can continue running for days or even months without ever building toward one single large release of energy, which is precisely why swarms so often defy the kind of clean, predictable decay pattern that a normal aftershock sequence follows. This fluid-driven mechanism is exactly why swarms are so strongly associated with geothermally active regions like Coso, where hot water and steam are already moving constantly through fractured underground rock as part of the area's natural geothermal system, providing exactly the kind of fluid pathway that can trigger and sustain this self-feeding pattern of small earthquakes. Now let's walk through the other 2 swarms that make up this recent cluster of 3, because understanding each one individually helps explain why seeing all 3 together within roughly 2 months genuinely stands out. The first of the 3 struck back in May, when an earthquake swarm erupted over a weekend in Southern California's Imperial County, in which hundreds of earthquakes shook the region, including a magnitude of 4, 7 tremor, that struck specifically on Mother's Day. By the following Monday morning, the Southern California Seismic Network had recorded 401 individual tremors as part of that single swarm. The largest earthquake in the sequence was that magnitude 4, 7th event which struck near Brawley, a town positioned north of the U.S.-Mexico border in California. Seismologists studying this specific swarm noted at the time that this kind of activity is far from unusual for the Imperial County region specifically, which sits at the southern end of the San Andreas Fault system, in an area known for exactly this kind of frequent fluid-driven swarm activity tied to the region's own significant geothermal resources, similar in underlying mechanism to what drives activity at Coso further north. Imperial County in particular has a genuinely long history of what seismologists sometimes refer to as the Brawley Seismic Zone, a section of crust where the plate boundary shifts from the more classic strike-slip motion of the San Andreas Fault to a more complex zone of distributed faulting connecting toward the Imperial Fault further south, an area that produces swarms with real regularity precisely because of how much fluid movement and geothermal activity is already occurring beneath the surface there. The second swarm in this sequence struck in July, this time much closer to the heart of the Eastern California Shear Zone itself. On July 13th, 2026, a new earthquake swarm began in a seismically active stretch of Southern California, with its epicenter located approximately 17 kilometers west-southwest of the small desert town of Johannesburg. The sequence started with a minor magnitude 1, 5 tremor at a depth of 6 kilometers, and over its initial 10 hours and 46 minutes, it went on to produce 28 separate earthquakes. Activity intensified dramatically in the afternoon when a sharp magnitude 4, 3 earthquakes struck at a depth of 7 kilometers, an event strong enough to be felt in the surrounding communities. That magnitude 4. 3 earthquake acted as a catalyst for a flurry of subsequent tremors, and in the hour that followed it alone, more than a dozen additional smaller earthquakes were recorded, ranging from magnitude 0, 5 up to 2. 2. This swarm, occurring in exactly the stretch of the Eastern California Shear Zone that includes the broader Ridgecrest Coso Garlock system, was explicitly tied by monitoring services to the same long-term pattern of increased seismic activity that has followed the 2019 Ridgecrest sequence, activity that strongly supports the hypothesis that the regional crust in this specific area is still actively responding to the major stress changes generated by that 2019 rupture, more than 6 years after the fact. So now, laying all 3 of these out together, you have a clear sequence. A swarm in Imperial County in May, producing over 400 individual tremors and a magnitude 4, 7 main shock. A swarm near Johannesburg in July, directly within the Eastern California Shear Zone, producing dozens of earthquakes topped by a magnitude 4, 3. And now this most recent swarm at the Coso volcanic field in August, sitting just north of the Garlock Fault, the exact location that has already been the site of 2 other earthquake swarms within this same general window of time. 3 swarms, across roughly 2 months, all connected either directly or through shared underlying tectonic mechanisms to the same broad stretch of Southern California desert that includes the Eastern California Shear Zone, the Garlock Fault, and the lingering aftermath of the 2019 Ridgecrest earthquake sequence. It's worth being very clear here about what seismologists are and are not saying about this specific pattern. Every single one of these 3 individual swarms has been described by the scientists studying it as on its own, not unusual for the specific region where it occurred. Imperial County swarms happen with real regularity given the area's geothermal activity. Coso swarms have happened repeatedly since 2019 and are a well-documented, well-understood feature of that specific volcanic field's response to regional stress changes. Swarms within the broader Eastern California Shear Zone near Ridgecrest and Johannesburg have become measurably more frequent since 2019 as well, exactly as the historical data comparing the pre-2019 and post-2019 periods clearly shows. No individual scientist studying any one of these 3 swarms in isolation raised significant alarm about it, representing an imminent threat on its own. But here is exactly where the nuance matters, and why the framing of 3 swarms in 2 months is genuinely worth taking seriously rather than dismissing outright. Individually unremarkable events, when they cluster together in both time and geographic proximity, become a meaningfully different kind of data point for scientists studying the broader regional stress field. Each of these 3 swarms represents a location where the crust released some amount of accumulated tectonic stress in a relatively short and localized burst through this specific fluid-driven mechanism, rather than through one larger, more classically structured earthquake. When you see 3 of these releases happening across the same broad region within a compressed time frame, it becomes reasonable and scientifically responsible to ask what that pattern might be telling you about how stress is currently being redistributed across the entire Eastern California Shear Zone, 6 years removed from the massive 2019 Ridgecrest rupture that originally reshaped the stress field across this whole area. This connects to a broader and genuinely important point about how the crust in a major fault system behaves in the years following a large earthquake. The 2019 Ridgecrest sequence didn't simply release energy and then leave the surrounding crust in a stable, settled state. Large earthquakes redistribute stress across an enormous area, sometimes loading additional stress onto nearby faults and fault segments that didn't rupture during the main event itself, while relieving stress on others. That redistributed stress doesn't simply vanish. It continues working through the surrounding crust for years, sometimes decades, as different fault segments and different geothermal systems throughout the affected region gradually adjust to their new stress state, often expressing that adjustment through exactly this kind of swarm activity. Since fluid-driven swarms are frequently the mechanism by which a stressed but not yet critically loaded fault segment releases smaller amounts of accumulated energy incrementally, rather than storing it up toward one larger, more dramatic release. This is precisely why the doubling, and in fact tripling, of swarm frequency in the Eastern California Shear Zone since 2019, from just 2 documented swarms across the 18 years between 2000 and 2018, to 6 separate swarms in the roughly 6.5 years since, is a data point scientists take seriously as evidence that this specific stretch of crust remains in an active, ongoing state of adjustment following that major rupture. The 3 swarms that have now occurred within just the past 2 months, Imperial County in May, Johannesburg in July, and Coso in August, represent the most recent and most concentrated expression of that same longer-term pattern. And it's exactly the kind of concentrated clustering that gives seismologists a genuine reason to watch this broader region more closely in the months ahead, even without any single event in the sequence rising to a level that would itself be considered a major earthquake. It's also worth understanding what swarms elsewhere in the world and throughout history have taught scientists about how these sequences can behave, because that broader context helps calibrate exactly how seriously to take a clustering pattern like the one Southern California has experienced this summer. Not every swarm fades away harmlessly. In South Korea, hydraulic stimulation at a geothermal energy project in Pohang generated a swarm that escalated to a magnitude 5 earthquake in 2017, occurring 2 months after the pumping operations that triggered the initial activity had already stopped, illustrating that injection or fluid-driven swarm sequences can sometimes continue building toward a larger event, even after the original triggering activity has ceased. A separate geothermal project in Basel, Switzerland, was permanently shut down after stimulation activity triggered a magnitude 3 earthquake back in 2006. A decision made specifically because of concerns about the unpredictable way that pore pressure increases and earthquake interactions within a swarm sequence can progressively weaken a fault, sometimes triggering larger events later in a sequence rather than earlier. A pattern worth noting, even though most swarms, including the ones discussed in this video, are naturally occurring rather than tied to industrial fluid injection. At Japan's Matsushiro region, a famous historical swarm that began in August of 1965, with 3 earthquakes too weak to be felt, escalated over the following months until, by April of 1966, a single observatory recorded 6,780 earthquakes in one day alone, with 585 of them large enough to be felt, meaning residents in the area were experiencing a noticeable earthquake roughly once every 2.5 minutes at the peak of that sequence, a swarm ultimately linked to an underlying magma uplift beneath the region. Closer to home, an earlier documented swarm in Arkansas, known as the Enola earthquake swarm, began with a magnitude 4 main shock in 2001, followed by approximately 2,500 additional earthquakes over the following 2 months, a sequence that produced a statistically unusual, linear cumulative seismicity pattern compared to typical swarms recorded elsewhere, and one that did cause some structural damage in the surrounding community when its activity picked back up the following May with another magnitude 4 event. To be clear, none of these more extreme historical examples are being presented as a direct prediction for what's currently happening in Southern California. The Coso, Johannesburg, and Imperial County swarms this year are all considerably smaller and less intense than the Pohang, Basel, Matsushiro, or Enola sequences, and California Volcano Observatory scientists have specifically and repeatedly confirmed that the activity at Coso remains tectonic rather than volcanic in origin, with no ground deformation detected that would suggest any kind of magma movement beneath the surface. What these historical examples do illustrate, however, is the genuine range of outcomes that swarm sequences are capable of producing, from the overwhelming majority that fade away within days or weeks without any further escalation, to the smaller number of documented cases where a swarm has continued building toward something larger over an extended period. This range of possible outcomes is precisely why seismologists don't simply dismiss swarm activity out of hand, even when any individual swarm, considered entirely on its own, looks unremarkable and well within the range of what the specific region has historically produced. It's worth taking a moment to explain how scientists actually track and identify these patterns in a systematic way, because this isn't simply a matter of someone noticing 3 headlines within a couple of months and drawing an informal connection between them. Researchers have developed dedicated cluster analysis tools specifically designed to formally identify and catalog earthquake swarms from raw seismic data, using specific parameters, including the minimum number of earthquakes required to constitute a swarm, the maximum distance allowed between consecutive earthquakes within a given sequence for them to be counted as part of the same swarm, and the maximum time gap allowed between those earthquakes as well. This kind of systematic, quantitative approach allows scientists to track swarm frequency across a specific region over long periods of time with genuine statistical rigor, which is exactly the methodology that produced the finding that swarm frequency in the Eastern California Shear Zone has tripled since the 2019 Ridgecrest sequence compared to the 18 years that preceded it. This isn't an informal impression. It's a documented, quantified shift in the behavior of this specific stretch of crust, based on a systematic comparison of swarm activity before and after a known major stress redistributing event. And similar cluster analysis methodologies are now being applied by researchers studying swarm behavior in other tectonic settings around the world, including along sections of the Mid-Atlantic Ridge, helping build an increasingly global, increasingly data-driven understanding of exactly how and why swarms form in such a wide variety of different tectonic environments. So, what does all of this actually mean for people living in or near this stretch of Southern California, spanning the Coso volcanic field, the Garlock Fault, the broader Eastern California Shear Zone, and Imperial County to the south? First, it's worth being clear that none of the 3 swarms discussed in this video have produced significant damage or injuries, and the strongest single earthquake among all 3 sequences, the magnitude 4. 7 near Brawley in May, while genuinely felt by residents in the surrounding area, falls well short of the magnitude threshold typically associated with serious structural damage. Second, understand that this region has an extensive, well-documented history of exactly this kind of swarm activity, and that the increased frequency observed since 2019 reflects the crust's ongoing gradual adjustment to a major earthquake that already happened, rather than necessarily signaling that a new major earthquake is specifically imminent. Third, and this is the genuinely important nuance, this doesn't mean the pattern should simply be waved away either, because a region actively experiencing this level of ongoing stress redistribution, evidenced by 3 separate swarms within just 2 months, is a region where the underlying fault network remains genuinely active and worth continued close monitoring. Precisely the kind of monitoring that the United States Geological Survey and the California Volcano Observatory are already conducting in real time. For anyone living in this specific region, the practical guidance remains consistent with standard earthquake preparedness recommendations for any active seismic zone in California. Know your specific proximity to the Garlock Fault and the broader Eastern California Shear Zone, and understand that swarms in this area, while historically common and usually harmless, do occur against the backdrop of a fault network capable of producing significant earthquakes, as the 2019 Ridgecrest sequence itself clearly demonstrated when it struck without the kind of extended, obvious warning period that some other major earthquakes have shown in hindsight. Keep a basic emergency kit on hand, including water, non-perishable food, a first aid kit, a flashlight, and a battery-powered or hand-crank radio sufficient to sustain your household for at least 72 hours without outside assistance, the same standard recommendation that applies across every seismically active region of California, regardless of current swarm activity. And stay informed through official channels like the United States Geological Survey and the California Volcano Observatory, rather than relying on informal speculation, since these are precisely the agencies conducting the kind of systematic quantitative monitoring described earlier in this video. And they are the first to know and the first to publicly communicate if any swarm sequence in this region begins showing signs of genuinely unusual behavior, including any ground deformation that might suggest a shift from tectonic to volcanic activity at Coso specifically. None of this is about generating panic over a pattern that every scientist studying it directly has described, event by event, as not unusual for the specific region in question. Southern California's Eastern California Shear Zone, the Garlock Fault, the Coso volcanic field, and Imperial County have all experienced swarm activity for decades, and the underlying fluid-driven mechanism behind these sequences is well understood, well documented, and generally resolves without escalating into anything more significant. But the specific clustering of 3 distinct swarms within roughly 2 months, spread across this same broadly connected tectonic system, and occurring against the backdrop of a documented, quantified increase in swarm frequency across this entire region since the 2019 Ridgecrest earthquake, is precisely the kind of pattern that earns closer scientific attention rather than a passing shrug. It's a genuine, real-time reminder that a major earthquake's effects don't simply end the moment the shaking from the main shock itself stops. They continue rippling through the surrounding crust for years afterward, showing up in exactly this kind of periodic, fluid-driven swarm activity as the broader fault network gradually works through the stress redistribution that a rupture as significant as the 2019 Ridgecrest sequence set in motion, sometimes for the better part of a decade or longer, before that redistribution process finally settles into a new, stable equilibrium. If breakdowns like this one, explaining the actual science behind why earthquake swarms behave so differently from the earthquakes most people are familiar with, are useful to you, take a moment to like this video and subscribe, because understanding the real mechanism behind a pattern like this is exactly the kind of clarity that helps separate genuine scientific signal from simple coincidence. Leave a comment with your thoughts below, especially if you live anywhere near the Eastern California Shear Zone, the Garlock Fault, Coso, or Imperial County, and have felt any of this activity firsthand, because that kind of on-the-ground perspective genuinely adds real value to a conversation like this one. And if you know anyone living in this stretch of Southern California, share this with them, because understanding that this region's crust is still actively working through the aftermath of the 2019 Ridgecrest earthquake more than 6 years later is exactly the kind of context that helps put a summer of clustered swarm activity into its proper, evidence-based perspective. 3 swarms in 2 months, all connected to the same broad tectonic system, is genuinely not the kind of pattern scientists ignore, even when every individual event within it looks, on its own, like business as usual. Stay informed and stay with us as we continue tracking seismic activity across this region in the days ahead.